Okay, so now we have one more demo for today. Now in this device, here you have a solenoid with many number of turns. And I have a conducting ring. This is also aluminum. It's not affected by, it doesn't stick to a magnet. Now what I will do is I will just turn on the current. What do you think will happen? Those that already know the answer, please don't answer. But the other ones, what do you think will happen when I turn on the current? So here is our solenoid. Let's say we send the current in this direction in the solenoid. What will be the direction of the magnetic field? In the upward direction. And then we have a ring around it. This is the ring, the aluminum ring. Now, what is the magnetic field initially? 0. So, B initial equal to 0. Well, it is in the upward direction, finally, is non-zero. So, the magnetic field is changing in time. So, we have a changing magnetic field. The magnitude is increasing in time. Well, the magnitude of the magnetic field is a positive number. Initially it is 0, finally it is non-zero, so it has to be increasing. So what should be the direction of the current induced in the wire, in the ring? Downward. This way? Or, let's just look at this side of the ring. The part that is visible. Will it go from left to right or right to left? Right to left. So this will be the induced current. Now, what is the force acting on it? Will there be a force acting on it? So, well, this is the system. There is no if. Is there a magnetic field or not? Will there be a force or not? Let's try it. Okay, so there will be a force. Do you want to see it again? Well, let's do one more thing. How high did it go before? 30 centimeters. Yeah, from here, 30 centimeters. Typical, maybe. So this is iron. So this is one effect that we will also study in a couple of weeks. So you see, initially, there's some effect. It just jumps. But when you put the iron, somehow the effect is enhanced. So somehow the magnetic field should be enhanced by the presence of this iron. So just keep this in mind. Let me try one more thing. Here I have another ring. Let me put both of them. Both of them are made from the same material. The other one stays. Let's try with these two rings. And let's see if one possibility is maybe if there are two rings, the one at the below just stays there. That might be the reason. Well, if you have two of them, they jump. But for some reason, not this one. Let me try one more thing. It doesn't jump. Well, the main difference between this ring and this one, they have the same weight. You can try it in the break. They are made from the same material, but this one has a cut through it. So basically, you cannot build this current. The current just cannot flow around the ring because there is an insulator somewhere on the ring. And that is why this one doesn't jump. Now, to understand that it should jump, we can also use the Lenz rule. Remember, Lenz rule says that the induced current is such that it tries to prevent what creates it. So in this example, if you just apply this principle, what creates this current is the magnetic flux that goes through the ring. So the ring basically will try to go away from the magnetic flux. Or it will push away, let's say, what is creating the magnetic flux. Well, it cannot push this object, it's quite heavy, so the only thing is it just jumps. So again, just using the Lenz principle, you can say that it should jump. Now, the question is what is the source of this force acting on this one? Okay, we said that there is a induced electric field. Okay, that I think we agreed. Now, what creates this force? Some of you said that it was the magnetic field, but we always say that outside the solenoid, the magnetic field is zero, at least on approximation. Well, the electric field, why should we have an upward electric field? Anyway, that is for you to think about. But this is let's say, the fact that we observe. When there is a solenoid, if we send some current through it, and when there is a ring on top, it jumps. Why? Well, inside there is a magnetic field, but the electrons will feel a force, or the the current will feel a force only due to the magnetic field where there is the current. So the magnetic field, the current here, let's say, if there is a current running through this wire, this metal, iron, it doesn't feel a force due to a magnetic field over there. It will only feel a force if there is a magnetic field at its position. So for this ring to feel a magnetic force, there has to be a magnetic field on this ring, at the position of this ring. The magnetic field inside the solenoid, I don't care about. Well, it doesn't care about it.
It's an enclosed magnetic field.
So, you see the force, when we write the force acting on a wire, if you remember the expression, it is I times dl cross B. The B appearing over here is at the position of dl, not some other magnetic field. You just take one segment of the wire, then determine your dl, and then you have to determine the magnetic field at the position of this dl, and that creates the force. So inside the solenoid, there's a magnetic field, but the ring would feel a magnetic force only if there is a magnetic field at the position of the ring.
When we do calculations, it's delta flux over delta T.
Well, that is for the EMF. That is EMF. And we said that, okay, from that EMF, we concluded that there should be this current. But how does this current create this force that causes it to jump?
Because we have an induced current,
Okay.
there will be an induced magnetic field.
Okay.
And the solenoid and the ring, they behave like a magnet.
Okay.
And the same force, they repel each other.
So, you see, this is the North Pole, this is the South Pole. If they were separate, that would be clear for me, that separate forces repel each other, they try to move away. But they're already overlapping. What happens if they're overlapping? Well, I see, if you would identify a North and the South Pole for the solenoid, you would say that this is the North Pole, this is the South Pole of the solenoid. And for the ring, this will be the North Pole, this would be the South Pole, right? So this is the current. So the magnetic field lines are going down, leaving from the down, coming back from the top. So the top is the South Pole, the bottom is the North Pole. Now, kind of on the contrary, I would say that there shouldn't be any force because North attracts South, South attracts North. Okay, that is for you to think about. Don't forget to hand in your homeworks. So let's continue. We have the solenoid example. If you remember, yesterday we solved the solenoid. Let's just review it. Okay, we assume that we have a solenoid which carries a current I, let's say in that direction. And then this current I creates a magnetic field inside the solenoid. What is the direction of this magnetic field? Towards you. This is the direction of the magnetic field created by the solenoid. And then we said that inside the solenoid and also outside the solenoid, there will be an induced electric field if we change the magnetic field. And so to determine the induced electric field, we first said that, okay, the magnetic field should be, magnetic field lines should be circular. So we assume the circular loop, and we tried to use the Faraday's law, which basically states that E dot dl around any closed loop, this should be equal to minus d phi b by dt, where phi b is the flux that goes through an area determined by this loop. So this is my loop over here. We said that, okay, let's just take the direction of dl to be this direction. And then we said that, okay, B will be in the same direction, induced B. So B dot induced E, sorry. E induced will be in the same direction or in the opposite direction. We don't know yet, but let's just assume that it's in the same direction. So E dot dl is just E induced times dl. And if you just integrate this around our loop, now E induced, we said that it can only depend on its distance from the center. So around this loop, E induced is just constant. I can take it out of the integral. And what remains is nothing but the circumference of this loop. If R is the radius, it's just E induced times 2 pi R. Now the flux is just area times the magnetic field because the magnetic field is uniform. Only for a uniform magnetic field, the total flux is just the magnetic field times the area. Otherwise, you have to consider it as an integral. Is it positive or negative? Well, let's see. We chose the direction of our loop to be clockwise. That determines the direction of the area. So just use your right hand, curl your fingers in the direction of your loop, clockwise sense. So this is the direction of the area vector, but the magnetic field is in the opposite direction. So the flux is negative, which is minus pi r squared, which is the area. And the magnetic field of a solenoid, we said that it is mu 0 I times N. Now we can use the Faraday's law. E induced times 2 pi r. This should be equal to minus d phi b by dt, which is pi r squared mu 0 I times N. And the induced electric field is equal to, well, pi's cancel, r's cancel one of them, mu 0 r, well, di by dt, mu 0 r n by 2 di by dt. This is if r is less than the radius of the solenoid. Well, if we are out of the solenoid, if we consider such a ring, Well, the derivation will be almost identical. The only difference is that this area now is just the area of the solenoid, not the area of my ring, because in this region, magnetic field is 0, or almost 0. So we can just ignore it. So in that case, the induced electric field times 2 pi r would be just pi large capital R squared mu 0 di by dt times n, which tells us that the induced electric field, this is pi. Pi is cancelled, mu 0 r squared over 2r n di by dt. Here. Well, you see what we have, this flux is nothing but the integral of the magnetic field over the area. Now whenever you think of the integral, it's just a sum of various contributions. So this is just the sum of b dot dA for r less than r plus the integral of b dot dA r larger than r. I'm just integrating inside the solenoid plus outside the solenoid. I'm just separating my two contributions. But outside the solenoid, magnetic field is 0. So this term is 0. Inside the solenoid, magnetic field is uniform. So I can just take it out. The area is just pi times capital R squared.
So originally the integral was from 0 to small r, but we divided the integral into pieces.
True. Because in this area, within this loop, the magnetic field is not uniform. There are two different regions. Each one of those regions have a uniform magnetic field. So just to simplify the calculation, I just divided my integral into these two regions. In one of them, there's a uniform non-zero magnetic field. In the other one, there is a uniform zero magnetic field.
Would we write the magnetic field as r and solve the single integral?
Sure. I mean, if magnetic field is position dependent, then this is what you should use. In this form or in some other form. So these are what we had for the magnetic field lines. If di by dt is positive, then you see the induced electric fields are positive in both cases. So we obtain electric field lines in this direction, both inside and outside. These are our induced electric field lines. And remember, the current is running in this direction, while running in that direction. Well, you see, we had calculated over here the induced electric field. We started by assuming that they are in the clockwise sense, and we obtained for the component in the clockwise direction to be positive. If di by dt was negative, then they would have been in the counterclockwise sense. Let's also draw that one. And if di by dt is negative, it will be in this direction. And in both cases, I was running in this direction. In one case, the current is increasing. In the other one, the current is decreasing. How did we create this current? The one that is running in the solenoid. By?
External battery.
By an external battery, which builds an electric field that pushes the charges around and creates such a current, right? So there's an electric field created by the battery, which tries to create this current. But now, if the battery is trying to increase the current, let's say, there's this additional electric field created by this induced electric field. At the position, on the wire, there's also an induced electric field. So it will also influence the current. So we have, if this is just a simple circuit, we have a solenoid over here, which we attach it to some resistor and some battery. There will be a current building up. And let's say that we are able to change the EMF as a function of time. We can increase it. If we increase this EMF as a function of time, we will be trying to increase the current. But if we try to increase the current, in this view, in the counterclockwise sense, there is an additional electric field created by this changing magnetic field, which will try to prevent the increase of the current, because it's running in the opposite direction. No, I don't really, I mean, just assume, for example, if you try to increase it linearly. There's no induced current yet, there's just one single current. The current is run by the electric field in the wire. The electric field will be created by the battery. So if you are trying to increase the current, you are trying to increase the electric field of the battery, created by the battery. But if the electric field created by the battery increases, the current will start to increase, the I by dt will be positive, and this increase in the current creates a magnetic field, induces an additional electric field, which is trying to push the current in the opposite direction. It will try to decrease the current. So there is a back EMF. So there is a resistance from this solenoid to an increase of the current. If you try to reduce the current, then it will be the opposite. Let's say the current is running in the counterclockwise sense. You somehow try to reduce the current, but then this reduction of the current creates an induced electric field, induces an electric field, and the direction of the electric field is such that it will try to increase the current. So if you try to reduce the current, this solenoid will resist it. If you try to reduce the current, the solenoid will again resist it. In a sense, it's just like the mass in mechanics. Remember what mass does. The mass, basically, if you try to push an object, if it's the mass, the more massive it is, it will slow it down. It will lower the acceleration. This is kind of an, in quotes, inertia for the changes in the electric field. How many of you have dogs? Dogs? Or you probably had some experience in dogs. I mean, living on campus, being on campus, that's kind of unavoidable, right? Dogs. Okay, so what they do, if you run, they follow you, right? So especially if you are afraid of the dogs, I mean, you will resist any change in any direction, right? So this is just like that thing. I mean, this magnetic field created by the currents, also remember the Lenz law. What it says is that the induced currents, and also the induced electric fields, by the way, will try to resist the change that creates them. So here, there are induced electric fields. The induced electric fields will try to resist whatever created them. It can be an increase in the current or a decrease in the current. But they're always in the direction such that they will resist any change. No. Well, what will be the electric field depends on how the current changes as a function of time. But you see, here we have a system. Let's just consider such a system. We will not solve it yet, at least not for a couple of more hours. Let's assume we have a solenoid. I mean, we will usually show it with this curly symbol. This is our, and we will also give it a different name. Let's also assume that we have a switch. Now, before, without this solenoid, the current as a function of time, we said that, okay, it will be 0 as long until the batteries, until the switch is closed. At this time, switch is closed. So the current will go to its maximum value. This is what we had said before, up to this point. But you see, here we say that the current is increasing infinitely fast. Let's go back. If the current were to increase infinitely fast, there will be an induced electric field which is infinitely large. But if there is an infinitely large electric field, I mean, it will just oppose the electric field created by the battery. So it just cannot be. So in reality, with the inductor, what actually happens again, there is nothing until the switch is closed. At this time, switch is closed. It cannot increase infinitely fast. It has to increase slowly. It will just increase slowly until it reaches the maximum value. And I0 is, again, epsilon over R. Eventually it reaches it, but it reaches it in a finite amount of time, not at 0 time. Why? Basically because this solenoid, or the general name, the inductor, resists changes. So it will just resist any change that you create. It will just resist any change that creates it. It will just slow it down. Now this is what we call an inductor. It's just a name. It is something that has a non-uniform flux. It resists, I mean, it's something that resists changes in the current. Now, let's see, let's stick with our solenoid example. Let's say there's a current running through it. Now, what is the total flux passing through the solenoid? You see, eventually what we will be using is epsilon is equal to minus d phi b by dt. So if there is a current running through the solenoid, if there is a current running through it, then there will be a magnetic flux running through it. passing through it. If there is a magnetic flux that changes in time, it will create a back EMF that would resist any changes in the current. Now, what is this flux? Now, let's just assume we have, well, this is our solenoid. It has a total of n turns. What is the flux? It has a radius r. Phi b is equal to pi r squared times b times n. Well, there are a few things you can say. And this will be our definition because we have n rings. Each ring has such a flux. This is the total flux. This is one way of looking at it. Or you can say that for each ring, there is a flux pi r squared b, but the total EMF created between these two edges will be the sum of the EMFs created by in each one of those rings. So then you multiply epsilon by n. But the convention is usually, if you have many rings, to calculate the flux, you just multiply it by the number of rings you have. You are just summing the flux that goes through each one of those rings. And we also know what B is. This is pi r squared n. And B, if you remember, it is mu 0 I times n. N turns. N is the number of turns per unit length. So the flux is equal to pi r squared n mu 0 n times I.
But why we didn't use capital N in the previous example?
Because there I only cared about the, you see, here I also use the small n over here to determine the magnetic field. This is the magnetic field. You see, in the previous example, I only considered one ring. I was just looking at one loop. Now here I'm looking at everything. Well, if you look at this term over there, it's just a property of your solenoid. It's not a, it doesn't depend on the current, it doesn't depend on anything that, any property of the circuit. It's a property of this device. That parameter that is for the special case of the solenoid is what we call L, inductance. The unit is Henry. So the flux passing through our device, we will just call it L times I. If you have a different geometry, of course the inductance will be different, but never, there will always be such an object. The flux basically, you see, the magnetic field will always be proportional to the current. And the proportionality constant will not depend on the current. It will only depend on the geometry. So the flux is just area times the magnetic field. Area depends only on the geometry. B is proportional to I. So whatever your geometry is, independent of how many turns you have, the flux passing through your device will always be proportional to the current. And that proportionality constant is what we call the inductance. So the EMF is putting in the signs minus L di by dt. So basically, if you have a circuit that contains an inductor, this device is called an inductor, which has an inductance. Just like you have resistors and which have resistances. And here we have an inductor that has an inductance. It will create you can also look at this in the form of you see, if you have a resistor and there is a current running through it, there will be a potential difference across the resistor, right? In the case of an inductor, if you have an inductor in your circuit, there will be again a potential difference in your inductor, across your inductor, if the current is changing in time. So this is the potential difference across your inductor. Yes?
Can I
Not really. Why do you think it is similar?
Because fixed capacitor to maintain the electric field. And now we have inductor maintain magnetic field.
In that sense, they are similar. Inductor in the magnetic field case is analogous to capacitor in the case of the electric field. So we can ask the question, in the case of the capacitor, we said, okay, what is the energy stored in the capacitor? That was something we had discussed. Now we can ask the same thing for the capacitor, because if we are trying to put a current in the capacitor will be resisting us. If we try to, because you start from zero current, if you want to build up a current passing through your inductor will resist you, and in order to be able to build up the current, you have to do some work against that resistance. So there you have to do some work, and that work will be stored in the inductor. Just like in the case of the capacitor, if you remember, in the case of the capacitor, we were building up a charge on the capacitor, and the more charge we put on the capacitor, we had to do some work to put charge on the capacitor, and that work was stored in the capacitor as electric energy. Now here, we have to do some work on the inductor to cause a current I pass through it. And that work that we had done is stored in the inductor as magnetic energy. Then the next question is, how much is this worth? Let's calculate it. We already know the EMF across an inductor. So what is the power? Epsilon I. Epsilon, let me just ignore the signs for the time being. It will just tell me that I am actually doing the work and the energy is stored in the inductor. So this is L di by dt times I. The work done is nothing but P dt, which is equal to Li di by dt times dt. Remember, the power is the work per unit time. So in a time dt, the total work done is nothing but power times dt, and I want to sum all the work that I have done. Well, here these I can cancel. Li di. Well, as I am doing work, the current, we are assuming that we start from zero current until we reach a final current I. So this is equal to 1 over 2 Li squared. So this is the energy stored in an inductor. Is equal to 1 over 2 L times I squared. Well, we can continue with the analogy with the capacitors. Again, if you remember the case of the capacitors. Now for the capacitor, if you remember, the analogous expression was 1 over 2 Q squared over C. This is the final charge on the capacitor. This is the final current running through the inductor. So if there is a current I running through the inductor, then that inductor already has an energy stored in it given by this expression. Now, in the case of the capacitor, we started from this one, and then we showed that this was actually equal to 1 over 2 epsilon 0 E squared times the volume of the capacitor. This is what we had shown before. Well, one can ask whether such a thing will be true in the inductor. So can we write the energy stored in the inductor as some energy density depending on the magnetic field times the volume of the inductor? Now let's see. To do that, let's remember the expression for L for an inductor. For the solenoid at least. That is one problem that we can solve explicitly. So this is our L. So the potential energy in the inductor, this is equal to 1 over 2 pi r squared n mu 0 n times I. This is equal to 1 over 2 pi r squared n mu 0 small n. I we can relate to the magnetic field in the inductor, which is nothing but B over I squared, B over mu 0 n. Remember, B is equal to mu 0 n times I. Of course, the square of the thing. This is equal to, well, mu 0s, one of them cancel, n, one of them cancel. 1 over 2 b squared over mu 0 pi r squared. Now, capital N is the total number of turns. So we can just write it as small n, the number of turns per unit length, times d. So I have this inductor. Let's call the height d, radius r. And I'm left with 1 over n. N's cancel. 1 over 2 b squared over mu 0 pi r squared d. Now, what is pi r squared d?
Area.
Pi r squared is the area, cross-sectional area, multiplied by the height. That's the volume of our solenoid. So we can just identify this 1 over 2 b squared over mu 0 as the energy density stored in the magnetic field. So just like energy can be stored in an electric field, energy can also be stored in a magnetic field. And again, this is also one hint that the magnetic field is actually a physical object, just like the electric field. It's not just our invention. They contain energy, just like any other matter that we know. Magnetic field lines, they are just our inventions. They don't have any physical existence. So yesterday when we were talking about the velocity of the magnetic field lines, that's just a visual aid to help you visualize what's going on. But magnetic field has a physical existence. It has the energy, and eventually we will see that it also has a momentum. Any questions before you go for a break?
Yes. What do you think about this? Something about the terms. We said that when we start the well, there is no conductor when we close the switch. What happens is that the current is increasing.
Well, if the current increases infinitely, the resistance of this inductor to an increase in the current will be infinite.
I understand that, but I would object to the fact that you said that current would increase. I don't think it does.
Well, in reality, of course not. You see, even if you don't put an inductor, is there a loop over here? So this loop, does it create a magnetic field inside in this area? So there is a magnetic flux passing through this loop, and you cannot change that magnetic flux instantly. Because even without the inductor, the wiring itself will have an inductance.
Yeah, I understand what you mean. What I was trying to say was even in any assumption, we need to think about that. fact that currents are not infinitely increasing, because it is bound by some speed, which is the speed of light.
Okay, I mean, we don't yet have the speed of light. In all of our discussions, the speed is infinite. So only in that approximation, in that assumption, it will increase infinitely fast. Other questions? It has been quite some time that we didn't have a quiz. The semester is approaching to an end. This is 5. That is a ring, a disk lying on the XY plane. And there is a uniform magnetic field and that is the positive direction of the ring. So this is the positive direction of the ring. This one. It is in a uniform magnetic field. So what is the magnetic flux? It is in the XY plane. It's in the ring is in the XY plane. The magnetic field is some direction like this. Just something like this. Well, in that sketch, it is some direction like this. It's not on the x-axis, not on the y, not on the z. You have 5 minutes for the quiz. After the quiz, you have 10 minutes for the break.